So welcome everyone to the 2023 February USACO solution discussion for the GOAT level. And today we will have the following agenda. We will first introduce XCamp quickly, and then go over the philosophy of XCamp teaching. And then after that, our coach Robert will explain the problems. And then after that, he will also talk about how to prepare not just for the US Open, but also use it next year to attend different XCamp classes to help you with the eventual the next season, right? And then there will be some QA section for you to ask some questions, either about the question, or maybe you can also ask something about the XCamp class if you are interested. So XCamp is a Silicon Valley-based coding academy. We provide the beginner level to the master level, which is camp level of United States, or IOI level of class, which is pretty unique across the whole country. And our curriculum has been developed by lots of seasoned coaches, IOI medalists, USACO veterans, NOI medalists, essentially lots of past strongest competitors, and it's proven in a sense that we already have a lot of students graduated out of the system in the past, and we have very solid knowledge for data structure and algorithm built for our students. And last season we had 4 US campers, and this season we have several students entered Platinum, and also we have several students in the top 10 in Platinum level as well. And we hope to help all the students to reach his or her potential. And we are hoping in the end of the day, our students will be able to change the world with coding, with the knowledge that we built for them. And a quick snippet of the XCamp teaching philosophy is that we treat coding education really seriously. And most importantly, we have 3 stages for coding education. The first stage is about beginner level to make students love coding. Second stage is to really pave the sort of make the road paved for algorithm and data structure to build the really solid foundation for students. At this stage, it's not competition yet. And the goal of this stage is to make sure you have complete knowledge, so students have a solid foundation for the college education and onwards, no matter it's a career in industry or graduate school study. And the third stage will be either go to competition, which is our Grandmaster class, to enter USACO higher level, or we will help you explore the engineering side of coding as well. And we are hoping the foundation you built at the second stage will help you to really help you in your college, right? And also in your career in the future. And we hope all students, you can have coding as the powerful skill to construct this lower bound of your life. That's it for the start of the talk. And then next, I will hand over to our coach, Robert. He will start to talk about the tutorial of the gold level of this of the February contest. Thank you.
Okay, thanks, Yuan. So I'm gonna share my screen right here so that I can. Oh, I need to. Give me 1 second. I need to relaunch Zoom so that I can share my screen.
Sure, no problem. Yeah, just quickly introduce Robert. He has been our 602, which is Grandmaster class coach for a long time. And in this season, there are 5 students entered the past the USACO Gold, entered the USACO Platinum for the first 2 contests. And we are hoping to recruit more and more students into our Grandmaster class to help you pass USACO Gold, which has becoming more challenging for the past 3 years. And we found this level to be very painful for students to pass. So we have very comprehensive curriculum constructed for this purpose, and we plan to have even stronger support in the incoming year. Yeah, and later I think part of this talk is about he will talk about the material, the questions, but in the same time, I'm hoping students here, no matter it's internal or external students of XCamp, I hope you can also focus on asking the coach how you can prepare either for the next contest, which is US Open, or for the next season as well. If you are not 11th grade yet, you still have the next season to do it, right? So I'm hoping you can explore that that too, and also make sure you talk to our coach to get your concern or planning answered as well, because that's even more valuable than several questions to be answered. Okay, I will hand over to our coach. Thank you.
Okay. Okay. So yeah, let's kind of like discuss like the solution for the 3 problems in this like USACO contest. So I'll start with like the problem 1 here, like and I will do it in order. So let's kind of like get a quick recap of like what problem 1 is about. So essentially, you are having okay. So the first problem here. So essentially, we are you're given an array of length n, and it's smaller or equal to 500, and the array is something like a1, a2 to an. Right. So each value it could be quite large, and the range is kind of like from negative 10 to the 5th to positive 10 to the 5th, 15th. So you are so they have this like restriction on the input saying that all the continuous subarray is kind of like different, have different sum. So you want to change one of the value here so that actually you need to solve n problem. For each of the n problem, you're given I, and then you want to find the minimum amount that you can change to AI so that there can be 2 different continuous subarray with the same sum. So for example, if you have an a input that is 2 and n equals to 2, and then the length is 2 negative 3. So essentially, what you want, for example, is like you can for example, for I equals to 1, you can kind of like decrease 2 by 2 so that the array becomes this, and then the sum of this subarray and this subarray is equal, right? And then for I equals to 2, so the solution for this is 2, because you can change this value by 2 so that there becomes like, and then you will have like 2 continuous subarray of the same sum. So in this case, it'll be 3, because you can kind of increase this number by 3 so that this array become 2 and 0. So in this case, you get 2 and 2, 0, which has the same sum. Yeah, so that's what the problem is asking. Like, so essentially you want to change some value so that you will have like 2 continuous subarray, 2 different continuous subarrays with equal sum. So let's think about this a little bit more, right? So suppose you are given such array. And you kind of like, so suppose you are solving I right now. I is somewhere in the middle, right? AI. So you want to change it so that you have this like continuous subarray, two continuous subarray that is the same. So let's think about how our solution might look like. So it is always a good thing to think in this way, which is if I increase this, where is it possible to get two different continuous subarray? So by that I mean, so for example, any subarray in this range, right? So you're already, suppose you're already changing the value of this one, and then any subarray belongs to this range will not change, right? Any of the subarray between this will not change, right? So you cannot say after changing this, I might get one array from this and one array from this that becomes equal, because all the sum doesn't change in this range, right? And I cannot say, okay, I might find two array that across this. So suppose I'm still changing this. I'm not gonna say I can choose, after I change this, it is possible to choose two subarray across AI so that they're the same. Because the reason of this is like, because they all contains this value, right? And before I change this value, it is they have different sum for those two subarrays, right? So if you change this number, the difference of the sum will not, if they are not equal, they cannot become equal, because you are changing the sum of the subarrays by the same amount, right? So what I'm saying here, right, is that there seems to be two kind of like subarray. One of them is like those subarrays, or subarray of those like subarray. Essentially, those sum will not change. And there's some other subarray. Essentially, all the subarray except those subarray that I mentioned is the second kind. So this is the first kind, this is the second kind. The second kind will only change exactly by the amount that you change it for AI, right? So essentially you get two kinds of subarray. One will stay the same, and then one will increase or decrease by a certain amount. And which means the only possible pair of the subarray, two subarray that you can choose, is must be one from this category and one from this category, right? Otherwise, they will change by the same amount or stays the same both way, which wouldn't make them like the same sum, right? So one of them must become this, belongs to this, and one of them must belongs to this. So this kind of like gives us a hint of how our solution might be, right? So suppose one of them is here, right? So essentially, you can have a sorted list of sum of those subarray and those subarray, right? So suppose they are 3, 7, 9, 10. Or probably making the gap a lot larger than this, right? So suppose those are the subarray with like larger, like that covers this element, right? So suppose the sum is probably like 12, 25, 48 or something, right? So suppose you have those two lists. Then what's the optimal solution to actually change this value by the minimum amount so that there exists some small some equal sum, right? So note that by changing this by some value, you are effectively adding all the elements here by x, and x could be like smaller than 0 or larger than 0, right? So greater than 0 or smaller than 0, right? So you can either increase them or right. So as you can see here, you're actually finding the numbers with the closest distance, right? Essentially, you choose two numbers that is closest, and then you can kind of like change this by the amount of their distance, right? So in this case, the optimal solution here would be plus -2, because you can kind of decrease those And in particular, you want to decrease this by 2 so that it kind of like match the sum of what you want, of the other list. So in this case, the answer is -2. So suppose we have those lists, right? It'll really, it'll be quite straightforward to actually get the answer. Yeah, so how do we get those lists, right? Or like what should be the way to actually represent those lists? So one way that we can do might not be fast enough is using a set, right? Because we kind of, okay, so we kind of want a sorted list or something, right? So suppose we keep them as a set here, and then each time, so let's see how we keep those set, right? So essentially, we're not gonna build those set each time we want it, because somehow we have this AI here, right? We have like at most like ON square different subarray. So each subarray is either gonna fall into this category or this category. So if we keep 2 sets and then we build it every time, it's gonna be really a little bit messy because you have to build n times, because you have to try different I here. And then for each of the subarray, the insertion of the set is n squared log n, right? So by building the set each time, you will have this worst complexity here. We'll go with that first. So it seems to be fast enough or not too bad for n equals to 200. So essentially, we build a set here, or build a list actually each time we want, and then build a list in this way as well. So we will have this list each time we want to solve this problem, right? I have to note that to quickly calculate the subarray sum, you cannot sum them brute-forcely. They're usually a better way called prefix sum array, which by now you should all know. Essentially, you can using ON preprocessing, you can get any array sum, subarray sum in ON. But so essentially for each index, you kind of like build a list, build those 2 lists together in n cube log n. And you don't even need a set here, because you can just like brute force sort all the things. So and after you build them, you can kind of like run some 2-pointer here, because effectively you are given 2 lists, and then you want to find the closest element here. So you have already sorted the list, so that you can kind of like, for this one, like you kind of like keep a pointer here, so that each time you kind of like are visiting a new element, you kind of like move the pointer so that you kind of know like which 2 element is closest to this in this list. So in this case, you will have an ON square for the comparison of 2 lists, because you have different AI to try. So in this part, like you will have n times n square, which is n cube. So the time is kind of like dominated by the time you use to sort the array, which I feel like is very sufficient for n equals to 200 or n smaller or equal to 200, right? So by then you will be able to solve like test cases 3, which is probably not enough and not that good in this task, because essentially what you don't want is to kind of like rebuild things together like again and again each time. So instead of that, what you can do is I will provide, I think I will provide several ways, two ways to do it. One of them is like you can kind of like keep a set of this. So when you are, so here's the thing. So once you have this set, it's easy to so just to note that, like remind you that suppose this is A, and then this is just like all the S and set minus A. So essentially all the subarray that doesn't belong to A belongs to the set below. So I'm gonna focus on how to keep this set, because you can kind of like do similar thing to keep the other set by just deleting things and then adding deleting old things and then adding new things, right? So let's talk about how to keep one of the lists here. So suppose you have a set here that is probably a multi-set in C++, keeping the sum here, which you're gonna use long here, because like the sum of the array can be really large. So essentially, suppose at the middle of the time, right? So you're solving AI, and then all the subarray in this range, like this, are all in S, and anything in this range is also in S, right? So what happens when you move to AI plus 1, right? So there's gonna be some new array here that the right endpoint is AI here, and left points can be something like this, right? So you're gonna add those in the set, which is fine. There is at most ON here, ON number here, right? The other thing is there's some array here that requires you to remove them from the set. Specifically, it's a subarray which has contained AI plus 1, right? So I'm gonna remove those things from the multi-set, and luckily there's also like at most ON such subarray to remove. So essentially you either cost your ON log n to like keep the set correct by inserting the things that are newly needed, and then eliminate the things that are not like exclusive to this element anymore, right? So you can do this update, and then as you can see, like the set is automatically sorted. So you can kind of like create an array based on kind of what you have for the multi-set, right? So because it's already sorted, by traversing it and inserting to a list, you will kind of like already get the sorted list as we mentioned before, right? So essentially this list, and you can construct the same thing here by keeping another set. Let's call it V, which essentially equals to all the subarray exclude S, right? So keep all the subarray that covers the current element, and then you can build the sorted array in ON as well. So in the end, you will get in this, you will kind of like get, oh, actually you will need to build them in n square, because this is a number of elements. So in this step, you'll get n square. So for each AI, right? So in the end, you will kind of have this complexity here, n squared plus n log n, which is dominated by the n cube term here. So that's pretty much the way to actually do it. So another way to do it is kind of like a set here. We can kind of like substitute here the set using some list. Essentially, it's not as intuitive as the set solution. So essentially, you are given a set, or we keep them in a sorted list, right? So each time we move from AI to AI plus 1, right? As I said before, you're gonna insert some array here and delete some subarray here. By deletion, you can kind of like find them in the list and then kind of delete them, and then rebuild the list only using those kind of like existing elements, right? But however, when you're inserting in list is kind of like a complicated game, right? So essentially, you're gonna insert them here, which each insertion will kind of like remove all the elements rightwards by 1 unit. So instead, what you can do is kind of like sort those elements beforehand, and that you want to insert beforehand, and then you kind of like have this merge sort like operation, right? So you have two sorted lists, and then you kind of like merge them together, and this will cost you like all the length of the sum of the length of those two array, which is like n squared in this case, in worst case, right? So essentially this will cost you like n times n squared in this as well for insertion. So note that it's kind of like slightly worse for the insertion than the set solution here, right? But overall you get the same complexity because in the end you are bottlenecked by the way that you kind of like traverse those lists. So even though you are keeping in this way, the complexity is still like n cubed. So I think n cube is quite sufficient for keeping for doing this problem. So since you have n to the 500, and then it's so as you can see, the constant is quite small, like because you are kind of like traversing the subarray. The subarray only have like n squared over 2 different. The array only have like n squared over 2, like around n squared over 2 subarray. So the constant is quite small here, and so n cube is quite sufficient for this task. So if you have any question, feel free to ask in the chat. If not, I'm just going to get to the next problem here. So